In 1985, LEGO came out with set number 1038, the Universal Buggy. To most people, the Buggy was a simple battery-powered vehicle. It had just 117 parts, two of which were 4.5-volt DC motors. By wiring each motor to a battery and manually turning the batteries on and off, you could make the Buggy move around by remote control. That would be fun for a little while, but there is much more to the story. A decade earlier, in the middle of the 1970s, came the personal microcomputer revolution. There were two categories of personal computers available back then. One was called S100, which were large desktop computers. Popular models included the MIT's Altair 8800 and IMSAI 8080. There were also smaller educational kits known as single-board computers, about the size of a few of today's laptops, stacked on top of each other. Popular models included the MOS Kim 1 and Heathkit ET3400. For either style computer, they usually came unassembled, so you had to put them together yourself. It's important to understand that by putting them together yourself, it's not like buying modern PC components, where you screw them into a case, plug in some connectors, and install an operating system. No, it was much more difficult than that. You had to know how to read an electrical schematic, know how to solder, and spend many hours meticulously connecting every wire by hand. Then, if it worked, you had to write most of the software by hand too. And almost nobody even had a keyboard or screen. The only input was to enter the commands and assembly code by flipping tiny switches or typing on a tiny hexadecimal keypad. If you were very lucky, you could afford to buy a teletype machine, which used inputs similar to a manual typewriter. Output was usually some flashing LEDs or simply holes punched into paper tape. Either way, it was exceedingly difficult, requiring tons of intelligence and patience to learn how to use this kind of computer. But even for the people who learned it, what could they do with it? There were all kinds of applications that people made, from games to business programs. Some people liked to connect their S100 single-board computers to the real world, such as controlling simple homemade robots. And if you're going to build a small computer-controlled robot in the 1970s, then a great way to get started was to build it from Lego. There were already Lego motors and technical parts, such as gears and axles, widely available. Lego wasn't necessarily the most popular option for the base of your robot, especially compared to robots made from metal parts, but it was feasible, accessible, and cost-effective. Designers at a Lego company realized that some hobbyists were doing this on their own, and that Lego competitors, such as Fisher Technic, were already getting ahead in technical models. Then, by the later part of the 1970s through the middle of the 1980s, Lego designers saw it became even easier for hobbyists to interface with their homemade robots by using pre-assembled home computers such as the Apple II, BBC Micro, Commodore 64, and IBM PC. In 1985, LEGO finally responded to this trend. They knew that in schools, teachers could show children some basic engineering and logic skills with the manual control of the Universal Buggy, including through the switches that came with set 1039. But they also knew that advanced hobbyists would find ways to wire personal computers to the Buggy. So while the Buggy was officially just a simple vehicle for kids to play with, LEGO designers knew that it would also help their company get started in robotics. An engineer who worked for LEGO back then told me that it was the fastest they ever went from having an idea for a new set to putting it into production. Now, let's build it. So our Buggy is now assembled, but how would it actually go about connecting it to a 1970s or early 1980s computer, especially a 1970s version, which is more fun? How will we do such a thing? To find out, let's talk to our friend Ethan Dix from the Columbus, Ohio Maker Foundry and producer of the Tonight's Hack blog on Facebook. Welcome, Ethan.
To start off with, all the computers of that era they use TTL voltages, typically 0 to 5 volts. And as you say, 4.5 volts is fine, but the real issue is that larger motors tend to be higher voltages, 9 volts, 12 volts. But no matter how you slice it, the amount of current that a motor consumes to move is far more than any standard TTL chip can push out. So the an IO chip that you would find in a KIM or a PET or a VIC-20, the 6522 or a 6530, that MOS series of IO chips, standard ports can put out a few milliamps. In fact, most of the ports aren't even strong enough to drive an LED all by themselves, let alone a motor. And so
I did read that these little Lego motors only require 0.1 amp, but that's more than you're saying still.
Right. Yeah. Then that is 100 milliamps. So the one exception to this, what they can provide, the 6522, which is found in a VIC-20 or a Commodore PET, the port that they present, the pins they present at the user port are specially high driver pins. They can put out 30 milliamps of current, which is plenty to run an LED, but it is not to run a motor. In fact, the spec sheets, I was just looking at this week, the spec sheets expect you to directly drive what's called a Darlington driver, which is where you take two transistors and one transistor drives the second transistor. And this was such a common arrangement where you basically step up your amplification that you could buy in back in the day, 3-lead Darlingtons, meaning there's two transistors inside one package, but still only 3 wires, because you're literally controlling one transistor in the package that controls the other transistor in the package that controls the outside world.
To ramp up the power.
Right. And that's what the MOS engineers had anticipated would routinely be connected up to port B pins on a 6522 VIA. 6530s, like you find in a KIM-1, or other pin ports like 6520s, PIAs, 6820s, like you find in like the Apple One, or then 6821, which is found in a lot of later machines, also PIA. They only have like between 1 and 5 milliamps, or even less. I think some of the ones I saw, the pins could drive 1/10 of 1 milliamp, 100 microamps. And those are literally meant to just control another TTL chip. So again, none of these can come close to driving a relay or a motor. So the usual arrangement is, if you're just going to turn a motor on and off in one direction, is you can put a Darlington on there, and you would tie the high end of the motor to whatever voltage you need at enough current to drive it. So, you were saying was 300 milliamps, I think, for the
0.1 amp.
Oh, 100 milliamps. 100 milliamps for the motor. So not a lot of current. But
and I also read that the official spec is, if you stop the motor, if you hold the axle, you hold the output shaft, it jumps up to a full.
Exactly. And I was about to say that then there's the stall speed, which is what happens when a kid grabs the axle. And and so that's, you have to worry about the stall speed, because in a robot like that, it's going to hit it at some point. You're going to run the robot against a wall, kid grab the wheel, you're going to get the stall speed. So you have to design for that maximum level of current. And probably, I'm trying to think back to what because one of the robots I worked with in the early 80s was the RB5X, and it has individual transistor drivers. They're in what's called the TO220 package. So they're about an inch long. They've got the heatsink tab on them, and they're a beefier package. But it just literally has four transistors under the down in the motor drive section. And then those transistors don't drive the motors directly. They drive 12-volt relays, and the 12-volt relays drive the motors. So that was for building a robot that's 1.5 feet tall and carries its own batteries and weighs quite a bit. So the motors are not low power. The Lego motors obviously are much, much lower power. They're much lighter weight, much less current. So you can probably, with that limitation, since you said the stall current is about 1 amp, you can get away with using a driver transistor to drive the relays, drive the motors directly. And but controlling it is just as simple as picking an output pin. And most of the machines of that era had some form of built-in parallel I/O. The Commodore PET had the user port, which was similar to what the Commodore 64 had, but just a few differences. But the eight primary pins were basically the same. VIC-20 had user port similar. The Kim 1, and I brought one here to show off, has built-in. I'm trying to think what they call it. It's it's an accessory port, but they've got a particular name for it, and I'm just blanking on the name right now. In fact, let me go and show that off. Kim 1.
Yep.
And the two ports are, the upper port is meant for memory expansion, so it has all the wires and all the leads and signals you would need for adding extra RAM, extra ROM, etc. And then the accessory port has power in. It has the connections for cassette tape for loading and saving programs. It has some keyboard connections. You can plug a teletype into this, so you can instead of using the keypad and the LEDs, you can literally have a teletype and save your programs on paper tape. And for the I/O chips up here, several of the I/O pins are routed directly to the accessory port, so that you can take advantage of unused I/O up in the main portion of the machine. And for that, I bought, before Corsham Technologies closed down, I picked up a power and I/O board, and it's still obviously under construction, but those I/O pins come out of this 26-pin connector here. And so in order to make that board drive a Lego motor, I would make a cable for this connector, then run that to an amplifier board. Again, today I have the choice of, they sell a number of 8-pin to 16-pin motor driver chips. You see those a lot in certain kinds of 3D printers, because they're very easy to use. You just give them a simple TTL signal and they'll drive the motor bidirectionally. Because I mentioned before, if you want to drive the motor in one direction, it's easy. You just turn 12 volts on or off. But if you want to run the motor backwards, you either have to have a source of minus 12 volts and turn that on and off, not at the same time as 12 volts. Or what you end up typically doing is you make an arrangement called an H bridge, which requires commonly 4 switching elements, whether they're transistors or relays, it's the same. And when you draw it out schematically, it kind of looks like a letter H. And you can basically have 2 inputs that go, enable the motor to spin one way or the other by switching the voltages on both sides of the motor, so that you still have your positive source voltage, but flips which pin of the motor gets that source voltage, so the motor spins clockwise or counterclockwise.
That makes sense.
Yeah, and again, these are all documented, in Micro, in Byte Magazine, and so on. People were doing this, and how to drive motors, and it's sort of thing where it's not hard to find, because it came up frequently. People were building robots. People were trying to drive all manner of motorized devices from microcomputers in the 70s and 80s, and it's just a common arrangement when you need bidirectional. The Lego Interface A has a similar circuit in it automatically for you, and that's why you can do the backwards forwards.
Right, and that circuit is on my website at brickaxe.com. Right. So how would this, I know you don't have one of these machines, but how would this differ if you're using an S100 computer instead of a single board computer?
So S100s typically had a different kind of I/O. They would routinely have, the most common chip in that era is a 8255, which is the Intel multi-IO chip. It has a port A, a port B, and a port C. It is nowhere near as flexible as the MOS series chips. Typically, you would tell an entire port to be 8 input bits or 8 output bits. But ultimately, you would probably end up either fabricating something from scratch, or you might be able to, they often sold S100 cards that were multiple printer, multiple serial ports. You would just get an I/O card that had all the I/O you might ever need, and you might steal some bits from your printer port, and rather than hooking up a Centronics type printer, you would run those wires out to your robot. Yeah, it's not as straightforward with an S100 box, because the nature of who was buying them, what they were using them for. You can find a few articles. Steve Ciarcia would routinely do I/O. The one that comes
the magazine was Circuit Seller, right?
Right, and before Circuit Seller, he had the Circuit Seller column in Byte Magazine.
In byte. Okay.
So going back to the 70s, there's one that I built, which was back when the game Simon first came out. They were really hard to get to find in stores because they were insanely popular. And so he had an article in.
You mean Simon as in boo 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 boo?
Right.
The lights
Simon as in
are
boop, 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 boop. Yep. Four colors and all that.
Okay.
And so there's an article that he build your own Simon, and he took an S100 CPM machine running BASIC, and half the article was how to construct the Simon, which was basically his actually made noise. So it was a pair of NAND gates and a capacitor and a resistor, which makes an oscillator, and he would tune it with a variable resistor. So he made 4 oscillators using 2 chips. He put on some transistors to drive light bulbs, because just like driving motors, most I/O pins can't even drive an incandescent light bulb, even a small flashlight bulb. You need the same sort of amplification. And then he had 4 input bits, which are easy, 4 resistors, 4 input bits. And then the rest of the article is a 1-page basic program to play Simon by using INP and OUT instructions to read and write a raw port on his S100 box.
It just occurred to me as you're saying that, how easy that would be to do with the Lego 8-bit system. That would be insanely easy.
Totally. Yeah. The only trick is that the input's a little tricky now because there's only 2 inputs on an interface A.
Run multiple interfaces, multiple cards.
Well, yeah, if you have multiple interfaces, it is very easy.
Yeah.
But the output side, very easy. So anyway, the point is that even Steve Ciarcia goes over how do you control simple, like a 4 input device from BASIC from a CPM machine. But you have to have the right kind of I/O board in your S100 box to do it to begin with.
Okay. Anything about this topic I haven't asked you that you feel it's important for my viewers to know?
Oh, let's see. I guess I can mention in the case of like depending on which era machine you're trying to hook up, if you have BASIC, routinely there is some way to do this I/O. In the case of 6502 BASIC, those machines tend to do memory mapped I/O, so you're almost sort of going to be using pokes. So just like you have shown with the how to drive an interface A from AppleSoft BASIC, the code is going to look very similar. Because ultimately what it comes down to is the card in your Apple is just a VIA sitting in an Apple card, and there is no difference on the software side whether you've got a Lego interface A hanging off of that card or your own invention with your own circuit hanging off of that card. The programming is exactly the same. You have input bits, you have output bits, and you're using poke to turn the bits on and off. The same would apply for any 6502 BASIC machine. In the case of a KIM 1, KIM 1s did not come with BASIC by default, and so you might end up resorting to assembly language. So you're going to be using, typically, LDA, STA instructions to hit the same registers. So it's going to be the equivalent version in assembly language of peeks and pokes.
But there was a BASIC you can get for KIM. I know, of course,
there was BASIC for KIM, absolutely, but not everybody had it. And if you've got the unexpanded 1K KIM, you're poking programs in on the keypad, and you're writing programs in assembler. Fortunately, some of the later machines, like the AIM65 or the SIM1, those routinely had more complicated bits. Lots of people who had an AIM65 had BASIC on theirs.
Okay.
And they also the SIM1 and the AIM also had very KIM compatible 44-pin ports, so you could even routinely take the exact same physical connector that you would plug into your KIM 1 and plug them into an AIM65, and it would just work the same way. The only possible difference is you might have to change your poke addresses.
Okay. And Ethan, do you want to give a shout out to your own your tonight's hack account?
Sure. I run a blog on Facebook called Tonight's Hack, and it's just as I repair things or find things or discover things, I just post little 1 to 3 photographs typically, and then a few lines of text about whatever I'm working on. And it's everything from mini computers to microcomputers to 3D printing. Occasionally home repairs and automobiles creep in there. Just anything I'm doing that involves mechanics, hands-on electronics, programming, that sort of thing.
And you also recently worked on the Interface B, the 16-bit Lego system.
Yeah, so I also picked up an Interface B, and because I am not a Windows user, part of the challenge for me was getting it to work with raw C code and compiling it for Linux, which I was able to do.
That all sounds like a lot of work. Fun, but a lot of work. So for now, keep that all in mind, and we're going to demonstrate the Buggy with the manual control, which is the version just for kids. Let's give it a try. I've got it parked here on my office floor, my home office floor, between 2 table legs. First, we're going to drive it out. And the first thing you'll see is it's easy to get it caught in the wires. So that's obviously a problem you have to watch out for. I'm going to press both of the up buttons, forward buttons, I should say. Now you'll notice it sort of pulled to the right a little bit. That's because it's pulling to the right. Apparently, I have many of these old 4.5 volt motors from the 80s, and they're worn out in different increments. So apparently the one on the left is a little bit stronger than the one on the right, and therefore it's always going to pull. I have maybe 9 or 10 of those motors. I'd have to just find 2 that are more similar in wear and tear, so it does that less. Anyway, it can back up if I press the 2 backward buttons. We'll go forward again. Now, if I let off the right forward and only press the left forward, it'll turn, and vice versa. But if I do it like a tank, where I do the left forward and the right reverse, it'll turn sharper. And the opposite. Pretty good spin there. Of course, I'm also limited by traction. It has the very, very thin little Lego rubber tires. In theory, if I put more of those on, or bigger ones, or at least fatter ones, it would get better grip on my laminated floor in my home office. Or if I had a floor that was grippier, like say carpet or concrete or something, it might grip better. Oh, going off camera. We don't want to do that. Spin her around. And back to its home. So here's how it works together. You see there's 4 buttons here and a battery box and a couple wires coming out. Battery box is the power, obviously. That is 3 1.5 volt batteries wired in series. There's 2 buttons per adapter. You can have as many adapters connected as you want. The manual shows 3. I'm not sure what you do with the third one exactly, but 2 is plenty for this application. And then 1 wire each goes to each of the motors. They provided these tiles of arrows in different colors: red, yellow, blue, white. I chose white. Simple enough. You press both forward, so this is the left motor and the right motor. Obviously, it'll move forward. Both reverse, it'll move reverse. Oh, sorry about that. If you accidentally press one a smidge harder than the other, or press one a smidge before the other, then it'll turn because it sees them as separate inputs. They actually have a manual description for how you would take a piece of like cardboard and make cutouts on them with a tab going across and turn it to get to both at the same time, but that was sort of a hokey idea. Anyway, if you turn left or right, now right now it's getting virtually no traction. These little rubber wheels on this table. Sorry about that. I suppose for this demo I should have put down a piece of cardboard or something. But if you do left, forward and right reverse, it'll spin. And again, oh, that one worked pretty well. It'll work much better in a moment when I show you on the floor. Anyway, that's the basics of how you control it. You can turn on either motor in either direction separately or at the same time.